Right. 2.46 is considered one of the canonical problems in quantum mechanics. And what I mean by that is that whenever you take a quantum mechanics course, regardless of what institution you take it at, assuming it's a legitimate institution, more likely than not, they are going to introduce this problem to you. It's a relatively simple problem, in my opinion. It's not that difficult to do, but it is considered a canonical problem in that it's part of the standardized sort of problem set that most classes would probably give you for homework. So it is pretty important to actually know how to do it. So we're told to imagine a bead of some mass m that's sliding frictionlessly around a circular wire ring with some circumference L. And we're told that this is basically exactly the same as a free particle since it's sliding frictionlessly, so v is equal to 0. And the only exception is that we have this boundary condition, which is that psi of x plus L has to equal psi of x. We're told to find the stationary states with proper normalization, along with the corresponding allowed energies. And then we're told that there are actually, with one exception, two independent solutions for each energy corresponding to clockwise and counterclockwise motion. We call them psi n plus and psi n minus, and we want to find each of them, respectively. And then finally, we want to explain this degeneracy in view of the theorem from problem 2.44, which stated that for one dimension, there can't be degenerate states for wave functions. So let's take this one at a time, starting with just finding the wave function itself. So for a free particle, the Schrodinger equation is going to read negative h bar squared over 2m times the second derivative of psi with respect to x squared, and it's going to equal e times psi. So v is going to equal 0 for a free particle, and it also equals 0 on this ring. If we solve this, we moved everything to the other side, d2 psi by dx squared is going to equal negative 2me over h bar squared psi, and we can rewrite this as psi is going to equal a e to the ikx plus b e to the negative ikx, as we've done so many times before when doing these kinds of problems, where k is equal to the square root of 2me divided by h bar. So now we have to add on the boundary conditions. So the whole point here is that that psi itself is effectively periodic. So it repeats after every interval of L. So we have this condition, psi of x plus L is equal to psi of x, but we also have the implied implicit condition for the derivative, which is that the derivative is also going to be sort of periodic because of the fact that the wave function itself is periodic. So psi prime at x plus L is also going to equal psi prime of x. So this second condition is sort of hidden in that it's not explicitly given to us, but it is something that we have to assume. Because remember, this wave function has two unknowns. We need two conditions in order to solve two unknowns. So because of that, we sort of add on this second condition. So now let's write this out. So we have the first condition, which is that a times e to the ikx plus b times e to the ikx is going to equal a times e to the ik of x plus L plus b times e to the ik of x plus L. And then we have the second condition for the derivative, which is going to be ik times a e to the ikx minus b e to the negative ikx. And you know what? This top term is supposed to be a negative. My apologies. And this is going to equal ik times a e to the ik x plus L minus b e to the negative ik x plus L. And now, unfortunately, this doesn't really help us yet because there's still too many variables and unknowns, primarily x. So let's consider the fact that we can sort of define an x term. Because remember, our range is going from x to L. So for reference, our base point is just going to be equal to x equals to 0. Because if we're looking at sort of a circle, then we're starting at some point and we're going a circumference of L around and ending back at that same point. So this point is our starting point. It's just going to be called x equals to 0. If we apply that to this boundary condition, then we have a plus b is equal to a e to the ikl plus b e to the negative ikl. And then we have the ik's cancel out of both sides of the bottom. We have a minus b is equal to a e to the ikl minus b e to the negative ikl. And at this point, from here, we can add or subtract to get two different conditions. So if we add, and you know what, let's write it this way. If we were to add this, we would get 2a is equal to 2a e to the ikl. And alternatively, if we were to subtract this, so let's take this and copy paste it over here, and alternatively we subtract it, then we get b minus negative b is 2b is equal to b minus negative b, so 2b e to the negative ikl. So at this point we have two conditions, and notably these two conditions are purely either in terms of a or purely in terms of b. Regardless of which one, we have this, in order for these to be true, we have e to the ikl has to equal 1, and e to the negative ikl has to equal negative 1. By using Euler's formula, we then know that this is basically telling us cosine of kl has to equal 1, and respectively cosine of kl has to equal negative 1. These two conditions evidently tell us the exact same thing, because cosine of negative kl is equal to cosine kl because of the fact that cosine is even. So therefore we have kl is going to equal 2 pi n, or k is equal to 2 pi n over L. Therefore k is equal to the square root of 2me divided by h bar, which is equal to 2 pi n over L. And then if I isolate for n, I get that the energy values for a bead on a string that forms a circular wire is going to be equal to 2 n squared pi squared h bar squared over ml squared, where n is equal to 1, 2, 3, and so on and so on. So we found the energies. The next thing we have to do is we have to find the wave function. And here is where sort of something special happens, because recognize that our two conditions for the energy are independent of each other. It's either a condition purely in A or a condition purely in B. What that implies is that allowing either A or B to equal 0 while keeping the other non-zero is a valid solution, since it would satisfy both of these conditions. Because remember, our two conditions are that e to the ikl equals 1 and e to the negative ikl equals 1. These two are effectively the same condition because of the fact that cosine is an even function. So there's nothing stopping us from saying that A is equal to 0, or that saying B is equal to 0, and letting the other one be non-zero, because everything is still satisfied. Alternatively, we can get the trivial solution by letting both A and B equal 0, in which case we would just get psi is equal to 0, which doesn't tell us anything. Alternatively, we can let both A and B be non-zero, but then that would just be a sort of linear combination of either A equals 0 solution or the B equals 0 solution, which sort of can be decomposed back into two linearly independent solutions. So effectively what this means is that there are actually two linearly independent wave function solutions, psi plus being equal to A e to the ikx, and psi minus being equal to A e to the negative ikx. Because the general solution is going to be the linear combination of psi plus psi minus. Hopefully this is familiar to you if you've taken, linear algebra. So this is what this is not A e to the negative ikx, it's B times e to the negative ikx. So the actual general solution is A e to the ikx plus B e to the negative ikx. But individually, these are valid solutions as well. So now what we have to do is we have to normalize. So if we set 1 is equal to the integral from 0 to L of psi plus minus dx, and we do this integral, well, the complex exponential cancels out, so this is equal to 0 to L of A squared dx, which is equal to integral from 0 to L of B squared dx, which is going to be A squared L, which is equal to B squared L. So therefore A is equal to B is equal to 1 over the square root of L. And with that, we have our wave functions. We have psi plus is equal to 1 over root L e to the ikx, and we have psi minus is equal to 1 over root L e to the negative ikx. And with that, we are done with the first half of this problem. Now, before I move on, I do want to make a few things clear, because what we see here seems to be very similar to what we found earlier with other sort of solutions that apparently don't have degeneracy. In particular, let's consider, for example, the infinite square well, a sine of, I believe it's kx plus b cosine kx, something like this. This is for the infinite well. So what we're going to ask here is that, if this apparently is valid as two linearly independent solutions, why is this not valid for two linearly independent solutions? Because, evidently I can, a sine kx and b cosine kx are linearly independent. Why does this not form two linearly independent solutions? And the answer to that comes primarily from sort of these conditions on k. Because here we have a condition on k that's purely in terms of a, and then a condition on k that's purely in terms of b. If you try to do the same analysis on something like an infinite well, you would find that the conditions you get have a and b being interlinked with each other. So therefore, as a result of that, it isn't valid to just allow one of them to equal 0 and assume that there's two linearly independent solutions like we're doing over here. Now, one more thing. How do we account for this degeneracy in view of the theorem from problem 2.44? So if you did 2.44, you'll remember that it talks about how in one dimension there cannot be degeneracy for wave functions. And here, evidently, we do have degeneracy in the form of twofold via psi plus and psi minus. So to explain this, the reason why is that remember that 2.44 required the wave function to be normalizable. Here, we have a wave function that is periodic, meaning it does not go to 0 infinitely far away. So if we were to try to normalize this, we would just get an integral from 0 to negative infinity to infinity of this would equal infinity, because the integral from negative infinity to infinity of the magnitude of psi plus minus squared dx is equal to infinity. Because it's going to be a magnitude squared, it's going to be an integral from negative infinity to infinity of a squared or b squared, and that integral obviously goes to infinity. So these wave functions are not normalizable. They are not physically realizable. They aren't physically valid. So because of that, this degeneracy can be allowed to sort of exist. Because once again, this is not a wave function that can actually occur in real life. So that explains why there's actually degeneracy. And let's see, find the stationary states corresponding allowed energies. Okay, now the final point. Note that there are, with one exception, two independent solutions for each energy. So what is the exception? So let's go back and look at our wave function, or let's go back and look at our Schrödinger equation. So the exception to the degeneracy actually is going to occur when e equals to 0. So if e is equal to 0, then we get 2 psi, d2 psi by dx squared is equal to 0, which implies that psi is equal to ax plus b, where a and b are not the same constants as before, they're new constants now. Now, traditionally, if we did this for most of the wave functions we found earlier, this would just give us a trivial solution, which is that psi is equal to 0, which doesn't mean anything. However, here we have the added condition that psi of x has to equal psi of x plus L, and psi of x derivative is equal to the derivative of psi at x plus L. And these two conditions result in the wave function actually not being just a trivial psi equals to 0. So if we write this out, we get, ax plus b is equal to ax plus L plus b. And then the derivative is going to be a is equal to a. So this doesn't tell us anything. It's a trivial result. But over here we have, ax plus b is equal to ax plus al plus b. So the b's cancel, the ax's cancel, and what we get is al is equal to 0, or a has to equal 0 because L is non-zero, which means that the wave function, instead of equaling 0, is actually just equal to a constant b. So this is a non-trivial solution. And physically, what this represents is, from x equals 0 to x equals L, we have a constant line as our wave function. So there's an equal chance for the particle to be everywhere along the wire. And this is obviously non-trivial, so this is the one exception, in that when energy is equal to 0, there's actually a non-trivial solution to the wave function, and it's not degenerate, unlike the positive values of the energy. And with that, we are done with this problem.